So I'm Katie Sidwell from RTDS Technologies, and I'm giving this webinar today with my colleague, Christian Jegs. My part is a presentation, which is mostly meant to introduce the concept of real-time simulation, and then go a little bit more into how it can be applied to the microgrid space, what our models and features are toward microgrids, and also include some real-world examples. So if you've been on our recent webinars, some of this will definitely be repeat information. So I apologize for that. After I'm finished speaking, after about 25 minutes, my colleague will do a live hardware in the loop demo from our office with a commercial automation controller. So we hope that'll be interesting for everyone, and we really encourage questions during that time as well. After this webinar, we'll be distributing a recording and a Q&A document, so stay tuned for that. So if you're not familiar with our company, RTDS Technologies is based in Winnipeg, Manitoba, which is a research hub for HVDC technology in Canada. And we were the world pioneer for real-time simulation in the 80s by creating our technology, which is called the RTDS Simulator. So today we have over 75 employees, and we have a high level of control over this technology. So our hardware and software development teams, our model development, customer support, our sales and marketing teams, and even our product assembly and our quality assurance testing, it's all in the same building. Before the emergence of real-time simulation, the main way of testing HVDC controls in the lab prior to deployment was by using something called analog simulators. So we've got some photos here of an analog simulator control room, as well as a machine room. So you can get an idea of how large these systems actually were. They were essentially scaled down physical models of the network of interest. So they operated inherently in real time because they were made of analog components. But they were prohibitively inflexible. So there was a need to reconfigure them physically for each study, and that could take weeks or even months. So there was definitely a need for a more flexible method, and that was really the main motivation for developing a digital solution. So a group at the Manitoba HVDC Research Center, which is also the home of the PSCAD software you might be familiar with, they ran the world's first real-time power system simulation in 1989, and then branched off to create RTDS Technologies. So today we have users in over 50 countries. We have 4 main categories of user: electric utilities, manufacturers, research and learning institutions, and consultants. So here's a look at just a few of over 100 utilities worldwide who are RTDS simulator users. There's definitely been an uptake of the technology by utilities who are operating microgrids. So I'll touch on a specific use case later on about that. Looking here at some manufacturing and research and educational users. So all of the major manufacturers of protection and control equipment are users of the RTDS simulator. This is just a subset of our user base in that area. And these folks have really integrated hardware in the loop testing into the factory acceptance testing of their equipment. And that kind of testing is more of an emerging area for microgrid control equipment. I'll touch on an example later on from SEL, whose services branch has used the RTDS for testing microgrid schemes prior to deployment. We also have well over 200 research and educational customers worldwide, a few of which are shown here. And I'll talk a little bit about the National Renewable Energy Laboratory later on. There are a lot of opportunities to apply this technology, and we've seen a huge array of different application areas develop over the last several years. We don't have time to touch on them today, but we do have some great technical publications and a wealth of information available about these. So please reach out if you're curious. But today we'll be focusing on microgrids. So you're probably familiar with some of the technical challenges associated with operating a microgrid. To operate autonomously during a disturbance while maximizing generation availability, preserving critical loads, and ensuring stability requires sophisticated control and sources that can provide primary frequency and voltage regulation to be among the many different resources that may exist in the microgrid. So coordinating all of these assets, which each have their own local controls, Layering a secondary control on top and operating with existing protection is an interoperability challenge. Also, high penetrations of renewables. We know that means intermittency, interactions between parallel inverters, systems with lower inertia and reduced ride-through, and changes to fault current contribution. All of which can create changes in power system dynamics and potentially cause instabilities in controller protection. So of course, vulnerabilities can be very costly to the operator, both financially and in terms of reputation. And on top of reliability and resilience issues, optimizing the control in order to maximize the performance, either economically or environmentally, is also a challenge. So today we'll discuss the role that real-time simulation can play as a modeling and testing tool in the microgrid space. And it's important to realize that this tool can really be involved at each tier of microgrid testing. So it can be used for testing primary level asset control. It can also test higher level coordination controls. And it can even be connected to higher level visualization tools that operate in the slower range. Maybe most importantly, it allows for validating the interoperability of these different tiers of devices. And it provides the ability to do so with real physical equipment. So different modeling tools are required at different stages of a microgrid project. For example, you might not see this type of work in the feasibility stage, but we're seeing more and more that EMT simulation and even hardware in the loop testing might be required in the tender as part of the validation process. So just to discuss a little bit about electromagnetic transient simulation, you might be familiar with different types of modeling, power system modeling. Load flow and transient stability analysis, for example, give you phasors around the fundamental frequency as an output. And this differentiates them from electromagnetic transient or EMT simulation, which provides a time-varying instantaneous value output. So the simulation output for an EMT simulation ideally gives you a waveform like the one shown here that would match the current or voltage waveform if it was measured from the real system. And this allows for a much greater depth of analysis over a wider frequency range and the ability to reproduce fast transients on the simulation. So the higher the sampling frequency of the simulation, the higher frequency results you can accurately reproduce. And the period of that sampling frequency, or the distance between two consecutive outputs, is called the simulation time step, or delta T, as shown here. And the typical time step with the RTDS simulator is in the 25 to 50 microsecond range, but we can represent the high frequency switching of power electronics, for example, in the 40 or 50 kilohertz range. And to do that, we use a much smaller time step. So why EMT simulation? For steady state analysis, phasor or RMS solutions do provide satisfactory results. Traditionally, they've been the most widely used type of model from a planning and operations perspective. That being said, existing technical codes are geared toward conventional grids that are dominated by synchronous machines. So when we get to systems like a microgrid with the presence of power electronics-based assets, we come across some issues here. RMS simulation lacks the ability to represent the low-level controls of inverter-based systems, and of course the ability to capture subcycle phenomena associated with transients. So we've seen increasing evidence that particularly in systems with a higher penetration of converter-based generation or loads, phasor simulation provides results that are too optimistic. So EMT simulation will be increasingly necessary, especially in the microgrid context, because it does provide more realistic results, and it's more likely to reliably predict things like control instability. So we know that we are using EMT simulation. What does it mean to operate that in real time? When we say real time, we mean that the computer needs to solve all of the equations for the network in real world time equal to or less than the simulation time step. And what that means is that the real time for a power system event to occur is equal to the time it takes to simulate it. So if you've used an offline, a PC-based simulation program, you know that the time that they take to simulate these events is either going to be slower, but more often, or faster, but more often much slower than the real event time. So that is one of the advantages of real-time simulation, its efficiency. When we're running longer simulations that might include slower acting dynamics or higher volumes of simulations, the simulation time could be very large using an offline tool. So using a real-time simulator can be tens or even hundreds of times faster for larger or more complex networks. So I hope that's clear what we mean when we say real-time. So beyond efficiency, the principal advantage of running in real time is the ability to connect external hardware in a closed loop with the simulated environment. So this means not only observing the response of a device to an imposed signal, but also interfacing that device's response back into the simulated network. And this is what we call hardware in the loop testing. It's only possible if we are updating the inputs and outputs of our simulation continuously in real time. It's not possible with a non-real-time modeling tool or with open loop testing tools like a relay test set. So open loop tools, they lack the flexibility to test multiple devices at once, for example, or to allow for detailed modeling of the network, for example, the inclusion of power electronics. In a microgrid environment with distributed energy resources and often multiple tiers of control, it's extremely valuable to be able to test interoperability and to predict interactions between different systems, and doing so with real physical devices. So unfortunately, the complexity of microgrids means that standard modeling or test practices could be blind to vulnerabilities in the system, and being able to reliably predict instabilities is the real value of HIL testing here. So to maintain real time is a challenge, and the processing power required to do so increases as the size and complexity of the network that you're simulating increases. So to achieve real time, the RTDS simulator is built on dedicated parallel processing hardware, which has been specifically integrated for the real-time application. So our current hardware generation is based on IBM's Power 8 processor, and we've developed it at the embedded level, so there's no underlying operating system, and we run our code bare metal on the processor. We achieve modularity through core licensing. So the quantity of cores licensed on a given unit determines the size and the complexity of the simulation it can run. You can run a simple microgrid simulation on a single core, or a much larger simulation with high detail on inverters by adding additional cores. And there's a link between the user's PC running our software and the simulation hardware. We use parallel processing on 2 levels. So inside a given unit, different cores of the processor are each dedicated to a different task in parallel to carry out the simulation. As the network size increases and we might exceed the processing resources for one unit, we can split the network into multiple connected subsystems. So we have parallel processing within each unit and between units for larger systems. In order to connect our simulation with external equipment, we use analog and digital input and output cards. So for example, here you see an analog output card which has 16-bit DACs, and that might be used, for example, to send power system voltage and currents to a protective relay. And similarly, we have cards for bulk digital signals. So you might use the digital input card, for example, to bring in external firing pulses for PWM schemes. It's also possible to create an interface with standard compliant communication protocols. So we've developed this network interface card to do so. It takes simulation data, assembles it into standard compliant packets, and then sends those out via Ethernet. And it can also unpack the inputs coming in from external devices. So these will be used in the demo later, so you'll be able to see it in action. We can directly stream the protocols listed here in real time. Today we'll be using DNP3 protocol as well as IEC 61850 GOOSE Messaging. I think it's useful just to see this diagram and get an idea of how the closed loop interface might look. So here we have a simple simulated network with a line that you can throw a fault on, instrument transformers, breakers, and sources. And we're taking our voltage and current off the line, bringing it outside of the simulation via the analog output card. Then we are using power amplifiers to provide secondary level signals to the relay. And then the relay contacts can then be wired back into the simulated breaker via digital input to close the loop. Okay, I'll speak a little bit about the software and get into some of our microgrid modeling as well. So RSCAD is our proprietary software. This is the operator's console shown here. So this is where the user can really dynamically interact with the simulation, apply contingencies, change parameters in real time, and collect data. There's also a scripting facility that allows the automation of large numbers of tests. We have a few conversion programs that allow users to directly import simulation cases from other programs. So we currently support conversion from PSCAD, PSSE, SIME, and MATLAB Simulink controls components. So SIME is a common distribution modeling tool, so that might be handy for users who are looking to do microgrid simulation. We have a very diverse power systems and controls component library. I won't go into it in detail today. I did want to mention that we have a component builder module for creating custom user-written controls or power system components, and those can then run in real time alongside library components. Microgrid modeling. So we have a wide variety of renewable energy models in RSCAD. Our wind turbine model allows the user to input wind speed and atmospheric conditions, define power coefficients, and some basic mechanical aspects of the turbine. And the turbine can be used to model several types of wind system design. The user can add induction machines, grid connection components, whether that's a direct transformer or power electronics. You can implement reactive power compensation, pitch angle control, startup and shutdown control, and we have sample cases available for a variety of configurations. So for example, the doubly fed induction generator case includes the induction machine, the back-to-back two-level converters, filters, everything required for both high and low-level control, including grid and rotor side converter DQ current control, and firing pulse generation. So that's all available. Our solar PV panel model allows installation and temperature inputs, and there's a couple of options for that model. It can be based on either the single diode 4-parameter model or 5-parameter model, depending on how the user wants to represent the voltage current relationship. And the model allows the user to program a shading pattern as well. And it does include maximum power point tracking. We have various options for energy storage modeling. So we have a PEM type fuel cell component with cell temperature and anode and cathode pressure as inputs. We have a lithium ion battery model. The focus there of the model is the electrical behavior of the battery. So it's not a detailed chemical model, but we do accept temperature as an input, and we can calculate the change in parameters according to temperature and state of charge. We have new mechanical energy storage sample cases as well. We have a flywheel and a pumped hydro storage case, and those cases are all documented and available in RSCAD. Our protection and automation library gives the user a lot of flexibility in combining physical and simulated relays in the microgrid testbed. So if certain protection or control functions aren't available physically, you can implement them in the software. And this library is also where you can find components for configuring Modbus, DNP protocols. We also have PMU simulation. So you can simulate a software PMU and provide its data either to another component internally for reference, or you can stream that PMU data to an external central controller. We also have environments for representing portions of the network at either a fraction or a multiple of the time step of the main network, and we call this multi-rate simulation. In the microgrid environment, if you are interested in the harmonic behavior, for example, of some converters or the high frequency interactions between those converters and the AC network, it's necessary to represent those converters in the substep environment. So for example, you can run your main network at 30 microseconds and a power electronic subnetwork at 3 microseconds. And on the flip side of that, we can choose portions of our network to simulate with a little less detail in the superstep network. So if we want to represent the utility network with more detail than just an infinite source, but we don't have the same requirements in terms of the frequency bandwidth of results, then we might represent that portion of the network with a time step of 150 microseconds. The substep environment has a variety of models for simulating power electronics. Many of these might be useful in a microgrid. 2 and 3 level bridges, boost and buck converters, VSC and MMC-based HVDC models. For most common topologies, we include resistively switched models. I won't get too much into the details of that, but it really allows the user to eliminate noise on the waveform and also to switch at higher frequencies without inducing artificial losses. So that could be very useful in the microgrid space as well. We also have options for simulating power electronics via average value models instead of fully switched substep models. So average models are essentially controlled voltage and current sources which sit in the main time step, not the substep environment. And they're able to accurately represent the real and reactive power profile of the inverter, both in steady state and transient conditions, but they don't represent the high frequency switching dynamics. So the controls for these models are the same as they are for the detailed models, right down to the modulation signals. They just don't allow for testing low-level firing pulse control. Power hardware in the loop simulation is the next step in closed loop testing. So here, the simulated network exchanges signals with a physical power device or a network extension in real time. And this type of interface is achieved via a 4-quadrant amplifier, such as those supplied by companies like Spitzenberger and Spies or Triphase. So this is particularly useful in the microgrid space because you can represent renewable energy components with a real physical inverter rather than a model. So in this example, we did some PV inverter testing in our office. And you can see in the diagram, we're taking the grid voltage, applying it to the terminals of a microinverter connected to a real solar panel, and then sensing that inverter current and sending it back into the simulation to close the loop. So this is a way to characterize the response of an inverter to various contingency scenarios prior to installing it on the grid. Moving on to some use cases before we get to our demo. UC San Diego has a campus microgrid, including a megawatt scale fuel cell, a large solar array, gas turbine cogeneration, battery storage, gas and steam plants, and emergency diesel generators as well. And their on-campus generation accounts for about 85% of their annual load. So during the 2011 blackout in the Southwest US, this microgrid disconnected from the main grid, but it didn't shed load quickly enough. So their co-generators shut down and they lost power to some of their critical loads. They have an on-campus hospital, for example. So to develop an improved control scheme in order to maintain power to those critical loads, they engaged with SEL Engineering Services. So on the left, you can see a diagram of the microgrid topology. You can see there are 3 utility ties, and this campus had the ability to split into multiple power islands, and the microgrid control system has been designed to track all of those islands and make logic decisions based on the topology. And SEL proposed this monitoring control system, which had over 100 devices consisting of controllers, protection, meters, visualization tools. It included some real-time automation controllers, similar to the one we will be testing later today. And on the right, you can see a communications network diagram with both slow and fast-moving protection and control data. So functionality here included primary and backup load shedding, peak shaving, generation control, adaptive protection, and an islanding detection and decoupling system. So here you can see the load selection process. So each load has a priority and they're doing hierarchical load shedding. It is set up to calculate the minimum load that's required to shed and keep the discrepancy between the actual load shed and the minimum to be very small. On the right, you can see the islanding detection and decoupling system for detecting loss of utility or decoupling in case of disturbances. The system has both status and analog-based components, and the analog scheme has a local component, which is based on standard protective relays for voltage and frequency, but also a wide area component. So I'm showing here their wide area component, which basically compares voltage angle at a remote bus in the utility 69 kV yard and at the microgrid's 12 kV switchgear. So SEL did dynamic performance testing of this system at their facility, which has an RTDS simulator, with folks from the campus present. So they used a mix of DNP3, GOOSE Messaging, and synchrophaser data, plus conventional analog and digital outputs. And they were able to test and validate the operations of the relays and the load shedding controller. Just a couple of results here showing the control system fulfilling its operational requirements. So on the left, we have a decoupling due to a frequency disturbance on the utility side, shedding about 5 megawatts of load, having that contingency-based load shedding kick in after the decouple. And on the right, they put it through some contingency chain reactions. So they had a fault trip the utility tiebreaker, and then it also caused the fuel cell, one of the steam generators, and a gas generator to trip within a few seconds. And load shedding was initialized, and they were able to stabilize the microgrid. Last case study is Borrego Springs, which is a small community located at the end of a single transmission line in California. So the utility, San Diego Gas and Electric, chose to develop a advanced microgrid controller for this substation. There was a high concentration of resident-owned rooftop solar PV, plus a large 26 megawatt, I believe, third-party owned commercial PV system. And actually that third-party owned solar facility elected to be part of the controlled assets for the project. So transitioning the operation of that facility to the utility was part of this project as well. So a secondary level controller from the manufacturer's SPI ray, shown in this diagram in blue, was interfaced with the simulated microgrid. And SDG&E did some testing at the National Renewable Energy Laboratory's Energy Systems Integration Facility. And they were able to test not only the microgrid controller, but also the diesel genset controllers, which you can see here as DG1 and DG2, and also physical renewable energy hardware. So they had PV and battery systems interfaced to the network as well. And this would have been a very challenging interface to develop and execute for several reasons, but it can be done. And the data manager gateway shown here acts as a communication protocol converter. So it's compatible with both DNP3 and Modbus, and it's able to communicate between the microgrid controller, distributed controllers, and the simulation. So various scenarios were simulated against the defined functional requirements for the controller. You can see there's 6 functional requirements listed here. Disconnection, can it decouple from the utility within a specified time frame for a different voltage or frequency threshold? Reconnection, does it delay synchronization until certain criteria are met? Protection, can the controller operate without unnecessarily tripping protection? So here you can see on the right, close to a 50% undervoltage event on the utility side. And we have the successful decoupling and recovery of the microgrid. When you see enhanced resilience there in the functional requirements, they basically input historical data from the utility of extreme weather events. So for example, they had a drop in solar insolation from 700 watts per meter squared to under 100 in less than 10 minutes. So they were able to take that insolation data, input it into the model, and see how the controller reacted. Okay, thank you so much for your attention, everyone. We are going to switch over to Christian's demo. Please feel free to open that Q&A window and ask some questions. We've been answering a couple privately during the webinar so far, and we'd be happy to answer more.
Okay, hopefully you guys can hear me. Are you able to see my screen? Maybe Katie, you can confirm that for me?
Yes, we can see your screen.
Okay, so today I'm going to be giving you a hardware and loop demo using a microgrid controller. And in today's demo, we're going to be using an SEL RTAC as our automation controller. Now, I just want to show a few slides to give a little bit of background information about the demonstration that we're going to be going through. So the microgrid system that we're going to be modeling and simulating within the RTDS is known as the Banshee microgrid. And it's based on an industrial facility with 3 radial feeders. You can see the microgrid is broken down into 3 separate feeders, and we designate the 3 separate feeders as 3 different areas. So on the leftmost side would be area 1, in the middle would be area 2, and on the rightmost side would be area 3. Now each of these feeders has different loads and generation assets available. So if we have a look at some of the loads, you can see these loads are designated with different letters. Here you see this load is I1, C1, P1. These are the load classifications of these different loads. So some of the loads are classified as interruptible loads, other loads classified as priority loads, and other loads are classified as critical loads. And these different load classifications are spread throughout the 3 areas. We have a look at areas 1 and 2. We can also see that we have some, 1 and 3. We can also see that we have some motor load present. If we look at the generation assets in each of the areas, area 1 has some diesel generation present. Area 2 has some battery energy storage as well as PV generation. And area 3 has a combined heat and power based generation. So this is the microgrid that we're going to be simulating inside the RTDS. Now let's talk about how we're actually going to interface the external controller with the RTDS. So we're going to be interfacing the SEL RTAC with the RTDS by using the GTNet X2 card that Katie had spoke about. Now this is a card that allows you to interface external equipment with the simulator by using various different communication protocols. In this particular example, the communication protocols that we're going to be using are the DNP3 and GOOSE Messaging protocols. So we're going to use these 2 protocols to exchange data between the microgrid model being simulated on the RTDS and the external microgrid controller. Okay. In the case of DNP, the microgrid model is going to be transmitting information to the microgrid controller. This could be various pieces of information such as the frequency measurements. It could also be the power flows of the generation and the power flows of the load. Okay. Conversely, the microgrid controller will also be transmitting values back to the RTDS using DNP3. And these could be things like power or voltage and frequency set points for the local controls of the generation assets in the RTDS. Now moving on to the GOOSE messaging protocol, in this case, the RTDS is going to be transmitting breaker status down to the microgrid controller so that the microgrid controller has a clear picture of the topology of the microgrid. The microgrid controller will then be sending the trip and close commands for each of the breakers in the network back to the RTDS using GOOSE messaging. Okay, so Now what I'd like to do is stop sharing my screen, and I'm going to turn on this video camera, and you can see me sitting there at our Zoom room here. And what I'd like to do is show you guys the test setup that we're going to be using today. So what we're going to be doing is we're going to be using this NovaCore simulator and GTNet card. So I'm going to get up and just power the simulator on here. So what we're going to be using today to simulate today's microgrid is this one NovaCore chassis shown here. Okay? To create the interface between the NovaCore and the RTAC, what we're going to be using is these GTNet cards shown here. Now what you see here is actually what's known as a GTNet chassis, and the GTNet chassis can host multiple GTNet cards. In our particular example, we'll only be using one of the 3 GTNet cards shown here. Again, the NovaCore chassis will be responsible for computing the simulation results of the microgrid in real time. Now, the device under test today is going to be the SEL RTAC, okay? This SEL RTAC is going to be functioning as our external microgrid controller, and it's going to be executing our microgrid controller code. And this external controller is interfaced to the RTDS by using an Ethernet-based connection, and it's going to be communicating with the simulator using the DNP3 and GOOSE Messaging protocols. Okay, so I'm back sharing my screen here. What I'd like to start doing is showing you the microgrid case within the RSCAD software. So this is the model of the Banshee microgrid within the RSCAD software. What you're viewing here is what's known as the draft module. And the draft module is where we would actually assemble the model of the power system. So what I'd like to do is just zoom in and show you a little bit about how these 3 areas are being modeled. So if we start with area 1, we can have a look at some of the loads and interconnection breakers that are present in the model. You can also see the classifications for the different loads shown here. So this load here would be classified as an interruptible load, whereas this load here would be classified as a critical load. Now, these load classifications will play into the load shedding algorithm for the microgrid controller when it's determining which loads need to be shed. So, all of the interruptible, priority, and critical loads are modeled using a dynamic load component. And these dynamic load components allow you to change the amount of power consumed by these loads as the simulation is running. Another thing we can notice in area 1 is our motor load. And our motor load is modeled using an induction machine. And then what we can do is we can use some control components to enter in the load characteristic of that load for this induction machine. We also see some normally open circuit breakers here, which are used to interconnect the various areas together. If we look at the generation asset in area 1, we can see we have our diesel generator that's modeled using a synchronous machine. If we go over to area 2 now, area 2 is the area that contains our renewable energy-based generation assets. And those generation assets are contained within these 2 boxes here. The battery energy storage is contained in this box here, and the PV panels are contained in this box here. If we have a look at how the battery energy storage system is being modeled, you can see that we're using the average value models to model the converters, okay? The DC side of which is supplied by the batteries. Now, the average value models still allow you to model and test all of the controls that you would normally find in an inverter. So what you can see here are the inner current controls as well as any outer loop controls. What these controls do is they generate a set of modulation waveforms, which are then used to control the sources within the average value model. Now, in the case of the battery energy storage system, we have two modes of control. One control mode is a PQ control mode, and is present when the battery is, or when area 2 is grid connected. If area 2 becomes islanded, the battery switches over from PQ control to voltage and frequency control, and the battery attempts to control the voltage of the islanded area in order to allow the other generation assets to remain connected. There's a similar type of philosophy that's applied for the PV model. The difference here is that the DC side of the average value model is then supplied by this PV component. We're able to enter in different parameters to the PV component, such as the insulation levels, the temperature, and we're also able to track the maximum power point required for this PV array. Again, if we have a look at the controls here, we can see that we're still able to model the inner current controls and the outer loop controls required for the PV panel, which means although we're using average value models here, we're still able to observe all of the transients and dynamics that would come from these controls. Lastly, we have area 3. Area 3, the combined heat and power is being modeled. Combined heat and power generation is being modeled using a synchronous machine. And similar to area 1, we also have a motor load here. Now that's just a quick overview of some of the basic layout of the case. What I'd like to do now is show you the components associated with the interface for the simulation case. And those components are contained in this hierarchy box here. Now, if we open this hierarchy box up, we can see the two GTNet components, one for the DNP3 communication protocol and another for the GOOSE Messaging communication protocol. Now, the data that's sent and received via DNP3 is defined in what's known as a points file. So I'm going to open that points file for you now. And this is a file that describes which points are going to be sent and received between the RTDS and the external microgrid controller. So I've made a little legend here to break down which points are going to be transmitted to the microgrid controller for each area. We see points 0 through 9 are reserved for PMU quantities, 10 to 19 for generation, 20 to 39 for loads, and the rest are reserved for future use. And then down here we can see the actual data points that are being sent out. So the frequency of area 1, the power flows at the point of interconnection, the power flows of the diesel generator, and the power flows of the loads. And this is similar type of process is done for all three areas. So down here at point 100, you see area 2. Here's the generation assets for area 2, and so on. Now, the external microgrid controller is going to be returning set points for the battery energy storage system, which are shown down here. So that covers the DNP3 communication. The GOOSE messaging communication, what we can do is we can look at which signals are being input and output of this component. So if we look at the signals that are being sent out of the RTDS and to the external microgrid controller, we can see that it's sending breaker statuses for each of the areas. So the breaker statuses for area 1, breaker statuses for area 2, and breaker statuses for area 3. Now the signals that are brought in from the external microgrid controller are these signals here. And we can see that each of the bits of these signals are mapped to trip and close commands for each of the individual circuit breakers. Lastly, I want to show you the PMU component that's being used in the case. So what we've done is we've used this PMU component to simulate 3 PMUs, one in each area. And these PMUs are used to provide the external microgrid controller with the measurement of the frequency in each area. Now let's have a look at what the simulation time step used for this case is by viewing the circuit options. Here you can see we've configured this to execute with a 30 microsecond time step. Another thing we can do is have a look at the hardware requirements for such a microgrid. We can do this by looking at this processor assignment chart. So here we can see that one of the cores is being used for the network solution. There's another core being used for the controls, and there's 2 more cores being used for all the remainder, or all the auxiliary power system components. So I would expect that if you had a 3-core RTDS, you would be able to stack this controls onto one of these existing cores for the power system components, and you would be able to run a model such as this. Okay. Next, what I want to do is move into the runtime environments and also the external environment for the microgrid controller. So this is the project for the external microgrid controller, and what we'd like to do is load this project onto the RTAC. So first what I'm going to do is clean the project. And then what I'd like to do is load this project onto the RTAC and put the RTAC online. So what I'm going to do is connect my computer to the RTAC and overwrite the existing settings on the RTAC. So it's indicating the settings have changed. Would I like to send the settings and overwrite? I click yes. Just take a moment here to send the settings to the RTAC. Okay, so it's attempting to connect to the runtime engine of the RTAC. Okay, so now it's connected to the runtime engine and the RTAC is online, which means I'm going to be able to view the RTAC as the project is being executed. Okay, now what I'd like to do is put the RTDS, begin the RTDS simulation. Okay, now the RTDS simulation is running. And now if we have a look at the RTAC project, we can see all of those data points that are sent via DNP now have some numerical values showing up in the RTAC. Okay. We can also see that the circuit breaker statuses are also being provided to the RTAC. True indicating a closed breaker and false indicating an open breaker. So for example, breakers 108 and 109 should be open. And we can view this by looking at the runtime canvas and viewing these icons. These icons here will change color as the breakers change state. So indeed, in area 1, we see that breakers 101, 102, 103, and so on are closed, and breakers 108 and 109 and 111 are open. So now what I'd like to do is I need to hand over control to the external microgrid controller. And I can do that by clicking this switch here. This will then indicate a true signal on the microgrid controller and start running the microgrid control. So if we look here, we can see some power flow from the grid to area 1. We can also see the diesel generation in area 1 is providing some power. You can also see the loads here are consuming power as well. Now, if we go over to area 2, we can have a look at what our renewable energy-based generation is doing, and we see that the battery is in the PQ mode of operation. If we have a look at the battery here, you can see that the state of charge of the battery is constant, and that there is very little current on the AC side of the converter. Well, what we can do now is we can go within our microgrid controller and we can command perhaps a new set point for the active power to have some current flow. So I command that set point and it's sent to the battery via DNP3, and you can see the battery is now commanding some active power. We now see some current flow on the AC side of the converter. And we also see that the state of charge of the battery is starting to go down. That's because the battery is injecting power into the network. We set the set point back to 0. We can see that the current goes away and the state of charge is now held constant again. We can also see that during this time, the PV is operating in the maximum power point tracking mode and happily injecting power into area 2. Next, what we would like to do is see what happens in area 2 if there's an islanding condition. And we can enforce that islanding condition by tripping this feeder breaker shown here. When we trip the feeder breaker, we would like to see that the battery would switch from the PQ mode to the voltage frequency mode and control the voltage and frequency of the island. So here we see the battery is switched over to the voltage and frequency mode, and the battery is controlling the voltage and frequency of the island, or the frequency here, to 59.8 hertz. By viewing this phasor diagram here, we can see the difference between the grid frequency and the voltage at the island. So we can see that the two phasors are similar in magnitude, but you can also see that there's a relative velocity between the two phasors, which indicates a difference in frequency. Now what we can do is we can go back in the microgrid controller and we can actually change the set point of the frequency for the battery. So let's change the set point from 59.8 hertz to, say, 59.9 hertz. Okay, we see the frequency is increased and the relative velocity between the two phasors is now diminished because they're closer in frequency. So next, what we'd like to do is reclose this feeder breaker and return to the grid connected mode. So we can do that within the microgrid controller by going to our trip and close commands. And what we would like to do is issue a close command for feeder breaker for area 2. So I'm going to issue the close command now. So I've issued the close command and you see the feeder breaker hasn't closed yet. Well, there's synchronization controls in this breaker that will only close once the two phasors have aligned. You see, once the phasors have aligned, the breaker closes and the battery is returned to the PQ mode of operation. Now, the synchronization controls in the case will monitor the slip frequency, the magnitude of the two voltages, and also the phase difference. Now, if we go over to area 1, we can do a similar type of experiment in area 1. In area 1, we have our diesel generation, and we also have several different types of loads. Again, critical loads, interruptible loads, and priority loads. So what we can do is we can island area 1 and observe whether or not our diesel generator changes its power, or if any of these loads are shut off by the load shedding algorithm. So let's do that now. So you see the frequency is begin to fall, and I see load I2 has been shed by the microgrid controller. Now we can see our frequency is stabilizing at about 59.5 hertz. Again, we can see the phasers rotating due to the difference of frequency on either side of the breaker. We can also see that the governor and exciter controls of our diesel generator have actuated and changed the P and Q, the amount of real and reactive power injected into the island. Okay? Again, if we'd like, we could issue the close command from the microgrid controller for this feeder breaker to reclose. We can also use the push buttons to do it locally. So if we do that, again, the synchronization controls does not allow the breaker to close until they are within the desired criteria. You can see that the interruptible load number 2 is still shed. And again, if we'd like to restore that load, we could do so from the microgrid controller by simply issuing a close command for breaker 107. And we see we've reconnected the load. So I hope this demonstration is useful for you to see how these different types of microgrid systems can be modeled in the RTDS, and how you can go about testing the higher level controls on an external microgrid controller, such as an SEL RTAC. You can observe how those controls interact with the local controls that are being modeled on the RTDS. With that, I'd like to conclude the demo.
Okay, thank you, Christian. That was great. I just want to clarify a couple of things that came up through the demo, and people can continue to submit Q&A if they have additional questions. The first thing I want to clarify is that that entire microgrid system that Christian was showing in the RSCAD software, it's simulated as one single subsystem with no decoupling. So that whole model is simulated on a single unit, and there's no need to decouple any part of that network with the traveling wave transmission line, for example. So in case people were curious about, I know that Christian showed the hardware allocation, showing the amount of hardware required to simulate it, but I just wanted to confirm that it is on one unit with no decoupling. I also wanted to talk a little bit about the physical interconnection layer between the simulator and the controller. Christian, I don't know if you have the capability to show your camera again, or to somehow show the physical connection. Oh, he's back.
I should be able to do that. The physical connection, it's really just an Ethernet cable connected from the back of the SEL RTAC. So there's a blue cable here. It's an Ethernet cable on the back of the RTAC. Now this cable goes into a switch inside the cabinet, and the NovaCore and the GTNet cards are connected to that same switch. I may be able to turn the cabinet around if you'd like, but
I think that's okay.
Okay.
Yep, I think that's clear. So there's an Ethernet connection. The NovaCore unit, the GTNet card, and the RTAC are all on the same switch. And that NovaCore unit passes data from the simulation to the GTNet card via optical cable. And then that GTNet card is sending the data out onto the LAN. So that's how that works. I believe we have answered all of the questions so far. We have a mention in the chat here. Christian has shown contingencies by hand, but it's also possible to automate predetermined scenarios for formal testing. Yes, thank you, Bruce. That's absolutely true. So Christian could write a script in the software that would basically allow him to automate a bunch of tests without interaction. So if he had to move a fault positioning or change the severity of a fault or a type, you could do that all via script. And if you are doing formal testing and you have a testing scenario plan, you could program that all into the simulator via scripts. Okay, we have several questions here, so I'm just going to read through of them a little bit. Okay, we have someone asking about the pumped hydro storage cases that I mentioned. Can't see that in the sample cases folder. So the reason for that is that those cases have just been developed and they will be released shortly. So they may not be available in the samples presently, but they will be available in the next point release as far as I know. So hopefully that answers that. What is the maximum time domain resolution of signals which we can view in the runtime in substep mode? Okay, that's a good question. So our substep time step can, sorry, one moment. Christian, did you want to answer that question?
This is, which question is that? Sorry.
Oh, sorry, it just disappeared. I was wondering if it was because you were answering it. So the question is what the maximum time domain resolution of signals which we can view in runtime for substep. So the answer is that in substep we can achieve substeps in the 1 microsecond range. We can also get into sub-microsecond time steps, that's possible. And you can, the resolution that you can see in runtime is each and every substep signal. So if you're simulating at 1 microsecond, you'd be able to go into runtime and see the resolution of the switching signal at 1 microsecond. I hope that answers that. We have a question about simulating a DC microgrid or a nanogrid. Christian, do you have any experience with that?
Not much, no. I don't think I can provide much comments on the DC microgrid.
Okay. Yeah, so it is theoretically possible to simulate a DC grid using the RTDS simulator. I don't have any experience with DC microgrid simulation, but it is possible. Okay, we have a question about online RSCAD certification, and we'll continue to answer these questions via text as well. I just wanted to cover some of them verbally for the group to save time. We have a question about online RSCAD certification. We don't currently offer RSCAD certification online. That is absolutely something that might be possible in the future that we are looking into, doing more online training. At the moment, we offer multiple training courses at our facility in Winnipeg every year. And we also offer training to customers on site when we provide the commissioning for the simulator. So those are our current modes of training. I think given current events, it's possible that we will have more online opportunities. So please sign up for our newsletter at rtds.com for more information about that. Okay, there was a question about PMU models. So not all PMU algorithms are the same. They vary by manufacturer. And do we apply sensitivities to the settings in our library model? So it was mentioned in the chat earlier, our PMU library models are generic models. So they're not vendor specific. And we're not too sure if we have done sensitivity studies to compare these models to certain vendor models of PMUs. We have a question asking us to show how to configure the GTNet card for different protocols. And I think that Christian showed that a little bit. So he showed the DNP configuration, for example, and that was done via a point mapping file that he created as a text file that was then referenced by the model. So I hope that was clear. I don't know, Christian, did you want to show, for example, the SCD editor? I don't know if we have time for that.
Yeah, the process for doing the mapping for GOOSE messaging is a little bit more involved because typically it'll involve the use of multiple softwares. So you do some of the mapping within the SEL tools. For example, you might use the SEL Architect tool to do some of the mapping. And you would also use our SCD editor tool to do the mapping on our side. So it's a combination of different tools in order to do that. It's not as simple as a simple points file.
Great, thank you. And if you have specific questions about configuring certain protocols, please contact us. You can go to our websites, and there's contact information there. And we'll also include some contact information in our follow-up email if you'd like to contact either Christian or myself. I think that's all the time we have for today. We're coming up on 15 minutes past the hour. So I just want to thank everyone for joining us today. We will stay online, and we have a couple of extra questions to get through in the Q&A by text. So we'll stay online to complete those. But I will wrap up the audio portion of the webinar. So thank you, Christian, and thank you everyone for joining us today.